Hi guys, this is chapter 2, part 3. We ended on accuracy and precision of the last screencast, and in your textbook you can see that they use the targets as well to explain the difference. You can go through them: high precision, high accuracy, high precision but not accurate, low precision, they're not close together, and low accuracy, and here is low precision but pretty high accuracy. Okay, the next concept is percent error. This is calculated by taking the accepted value. Say if you did an experiment and we expected to get like 10 grams of zinc, for example, but we only got 8 grams. So you do 10 grams minus 8 grams divided by what we were supposed to get, which was 10, times 100, to determine how close we are to the accepted value. So we'll use this a lot throughout the year to figure out how close we are in our calculations, and we're never going to be 100% because there's always some like substance loss due to measuring, or if it turns into a gas, it will escape into the atmosphere, or it's stuck on our test tube or something. So never get 100%, but that's okay. But we need to be pretty close to 100%. So here is accuracy and precision as well. In your PowerPoint. And percent error right here, the accepted value minus the experimental divided by the accepted. So let's go through an example. A student measures the mass and volume of a substance and calculates its density, 1.4 grams per milliliter. So this unit of density is mass over volume, like always, but they use grams and they put milliliters. So that's fine. The correct or accepted value of the density is 1.3. So doing this, they should have got 1.3. So we need to determine what is the percent error of the student's measurement. So using the equation that we just learned, it's the accepted minus the experimental divided by the accepted, multiplied by 100. So the accepted is 1.3. It's accepted or the expected, like you're expected to get 1.3. Minus 1.4 is what we got in the experiment, divided by the accepted is 1.3, and then you multiply it by 100. So the percent error is negative 7.7, and that is all right because that's pretty small. So we want a small percent error because you don't want to have any mistakes at all. All right, moving on to sig figs, significant figures. And once you understand this, you got it. But some students really struggle with it because they're like, why do we care about this? We care about it because you have to be as accurate as your measurements. So, and when other scientists look at your work, maybe you will be a scientist where other people look at your work, then they need to know how accurate and how precise the measurements that you used. So we all have to be on the same page. So significant figures is a measurement consists of all the digits known based on whatever you're using to measure it, plus one final digit that is an estimation that is uncertain. So sometimes like the calculator might spit out a number that is like 10 digits long. We're not going to use that because the calculator doesn't understand significant figures. It just like gives you 3 infinity. So, but as humans, as people, we know that the measurements, like whatever the ruler, we can't like say that this is 6.76523221 because we don't know that. So we only are going to have one estimated value. So for this measurement right here, you know it's 6, so that is certain. You know it's 123.3, that's certain, but the uncertain number is in between that 3 and that 4. So we have to have one more estimated value. So you might think it's right in between them. So you might put 6.35, or you might put 6. You might think it's a little over towards the next line. So you might put 6.36. So in here we have one estimated value, which is that 6. When we figure out how many sig figs there are, we're going to count all of them. So there's 3 sig figs. So we know that. And when we do calculations with them, like adding, subtracting, we can't be more accurate than the measurements that we started with, that we used to multiply, divide, or whatever. So when you're taking measurements, like in the lab, don't be more accurate than the instrument that you're using to measure. So in the lab, you'll do 6.35 or 6. So don't put 6.35421 centimeters, because that is not correct. Okay, significant figures. Sometimes we'll have these numbers, these measurements, that we have to determine how many sig figs there are in order to do calculations with them. So there's some rules that significant figures go by. And once you get them, you get them. So just be patient, and we're going to do a lot of practice with this, and then you'll get them. Indicates how precise the measurement is. So that's what sig figs are. Okay, the rules. Number 1, zeros between other non-zero digits are significant. So non-zero digits are any number that's not 0. And zeros are obviously zeros. So if you have a number and you have zeros in between non-zero numbers, you count the zeros as significant because they're kind of placeholders there. So whenever someone was measuring this, they knew that the ones place right here was a 0 before they measured 0.3. So that's why it's significant. So 50.3 has 3 sig figs because you count the 5, you count the 0, and you count the 3. So it's 3. B, 3.0025 seconds have 5 sig figs because you count the 3, 0, 0, 2, 5, since the zeros are in between non-zero numbers. Okay, rule number 2, and you can see that this mostly deals with zeros. Zeros in front of non-zero digits are not significant. So 0.892 kilograms. And you might think, well, that they should know that this is a 0 before they measure 0.8. The reason why it's not is because that kilogram can be converted into grams. And when you convert it to grams, you move the decimal point to the right 3 spots. So 0.892 kilograms is equal to 892 grams. And that number only has 3 sig figs. So that's why you don't count the zeros in the front of a number. You just don't count them. So this 0 you don't count, this 0, 0, 0, 0 you don't count. So this measurement has 3 sig figs. This measurement has only 1 because you don't count the zeros in front. And this is milliseconds. So if we wanted to go up to, well, not seconds, because then it would be 0.8. But if we wanted to do decaseconds, then it would be 8 decaseconds. So obviously there's only 1 sig fig in that measurement. So that's why we don't count the zeros. Rule number 3, zeros that are at the end of a number and also to the right of a decimal are significant. So these zeros are at the end and they're also to the right of the decimal. So they're significant. So that means that whoever was measuring this number, they put these zeros here intentionally because they had an instrument that measured all the way out to this, well, this one, and then this was your estimated value. So because the zeros are present, whoever measured it said that that 10th place or 100th place is a 0. So that's why they're significant. That's why they count as being accurate. So 57.00 grams has 4 sig figs. You count all the zeros. 2.00000 has 7 sig figs because you count all the zeros. And then rule number 4, zeros at the end of a number but to the left of a decimal are significant if they have been measured or are at the first estimated digit. If not, they're not significant. Now that rule doesn't really make sense. It just means that if there's no decimal point here, then that means these are not significant. So that's how we'll write it. We'll put a decimal point if we know that all these digits are zeros. So here you don't count the zeros, that's 1 sig fig. Don't count the zeros, that's 1 sig fig. Okay, we'll pick it up from there.